When engineering teams transition to building autonomous agents, they often make a structural error. They assume building a production agent just means handing the LLM a massive list of function tools. To understand why this fails, look at how a standard LangChain tool operates in the request cycle. The tool only executes after the model has analyzed the prompt, made a decision, and generated a tool call response. By the time the tool function actually runs, the model has already committed to its course of action. It is an after-the-fact execution. A plain function tool is invoked by the model. It cannot intercept the prompt, it cannot rewrite the visible tool list dynamically, and it cannot edit conversation history before the LLM sees it. LangChain's Deep Agents SDK addresses this limitation by taking a different architectural approach. It does not rip out and replace the underlying state graph. Instead, it intercepts the request flow. Deep Agents introduces an ordered middleware stack hooked into wrap model call. In this architecture, every single request hits this stack first. This intercept happens before the LLM formulates a response. The middleware evaluates the state, mutates the tool list, and curates the system prompt before the data packet ever reaches the provider. Relying purely on function tools surrenders system control to the model. A middleware architecture pulls state, security, and context out of the prompt and places it directly back into the hands of the systems architect. To see how this interception actually governs the agent, we have to look at how it integrates with the underlying state machine. The architecture is a three-layer split. At the base is LangGraph, managing state and checkpoints. The middle layer is LangChain's create agent, driving the model-to-tool React loop. On top is the Deep Agents SDK. It authors no loop, acting as a harness dictating the rules. A single assembly point, create deep agent, wires these layers together and passes execution down to the graph. Delegating the loop means you inherit a specific set of operational risks, namely runaway executions in long-running agents. The compiled graph ships with a recursion limit of 9,999. In practice, this means the loop is unbounded. It terminates only when the model stops emitting tool calls. Running a model for thousands of turns creates an immediate mathematical problem with state bloat. Standard message channels copy history, leading to O(n)² checkpoint growth. To solve this, Deep Agent State replaces the standard channel with a custom delta channel reducer, keeping data storage strictly linear over long threads. Because the runtime is effectively unbounded, the harness cannot rely on the loop to police itself. The safety and stability of the agent rely entirely on how the middleware stack is ordered and enforced. This middleware stack evaluates in a specific, deliberate sequence. Certain parts are locked into place. The file system and SubAgent blocks are required scaffolding. Attempting to drop either block raises a value error, refusing to build the agent. This strict enforcement exists because the file system block handles the absolute security guarantees for path permissions, while the SubAgent block backs the internal task delegation tools. The tail end of the stack manages context and caching. The provider prompt caching middleware sits deliberately above memory. Memory updates dynamically every turn. Positioning it at the bottom ensures these volatile updates do not invalidate the static prompt cache prefix established above it. An agent harness must be treated as a strict pipeline. This precise ordering guarantees both uncompromised security policies and optimized LLM context performance. This ordering also defines how the system interacts with the host environment. Production security splits the trust boundary into two vectors: execution, dictating where code runs, and authorization, dictating if it is allowed to run. The backend is the ultimate trust boundary for execution. The default state backend operates entirely in memory and cannot execute code at all. However, if developers opt for the convenient local shell backend, the agent gains direct host shell access with zero OS-level isolation. True isolation requires plugging in a base sandbox. The SDK offers no default sandbox. Providing secure isolation is entirely the developer's responsibility. The second vector is authorization, handled exclusively by permissions. Permissions evaluate path-based file system rules: allow, deny, or interrupt. This separates buildability from policy. A dangerous tool remains visible to the model, but middleware applies policy before execution. Hitting an interrupt rule pauses the loop, synthesizing a human-in-the-loop gate for manual approval. By decoupling execution from authorization, the middleware acts as an absolute physical barrier. Even if the LLM hallucinates a catastrophic shell command, the policy intercepts it before the backend can run it. Despite this architectural rigor, Deep Agents ships with a highly trusting default posture. The agent operates unsandboxed, iterating up to 9,999 times. This open-ended execution model collides directly with how the harness manages memory through a flat markdown file. Because this memory file is strictly append-only, with no built-in eviction algorithms or time-to-live tiers, stale or inaccurate facts persist indefinitely. They become zombie memory, injected into the system prompt turn after turn. Left unchecked, an unbounded React loop reading from an expanding, unverified text file will inevitably suffer from context rot. To safely terminate an unbounded loop, the system requires a programmatic gate to check the work before it accepts a final answer. Deep Agents addresses this with rubric middleware. When the main agent signals completion, a greater subagent evaluates the transcript. If it fails, the greater issues a needs revision verdict, injecting feedback into the history and forcing the main agent to resume. A production agent harness is not measured by the quantity of function tools it provides, but by the rigidity of its middleware. It wrests control of state, context, and termination away from the LLM, placing it exactly where it belongs.